or in your day-to-day life, you are observing that the amplitude of this oscillation decreases. Suppose, I think all of you have done that experiment tuning fork. After the first vibration, you are thinking that, or you are observing that the amplitude of vibration decreases, and finally it becomes zero. Why? As time passes on, its energy decreases. Energy means we can say that amplitude also, because energy is directly proportional to amplitude square. So energy as well as amplitude decreases. Finally, we have got zero oscillation. So if there is no external force, applied to the system, and the energy of the body decreases automatically. Automatically means what we are saying, that suppose your simple pendulum, it is vibrating in the medium. Tuning fork, it is vibrating in the medium. Then what happens? As it vibrate or motion started, there is some friction in the medium. So these frictional forces reduces the energy or destroy the energy. Similarly, while it is vibrating, some radiation energy is also emitting. So basically, due to this friction as well as radiation, the energy of the vibrating body or oscillator or oscillating body decreases. And since we have not applied any external force to the system, that is why it is known as free damped oscillation. Amplitude is damping, or energy is damping or decreases, but even if in the absence of any external forces, that is why it is known as free damped oscillation. Now, mathematically, or analysis of a free damped oscillator, let us consider a body. So first, all of you draw the diagram. This is the body, rest is here. Having mass M, and here one damper is present. And another thing is that body is with Kx massless spring, we can say. That is, this is elastic force. This is the damper, and this damping force is directly proportional to velocity with a negative sign, that means opposite direction. And here we can say that inertial mass md square x by dt square, inertial force. This is inertial force. Let us consider a damped harmonic oscillator which has 1 degree of freedom, and means it is vibrating or oscillating, or its motion is along one direction, x-axis. Let it is displaced a distance x from the equilibrium position. If we consider it is equilibrium position, it is displaced a distance x from the equilibrium position and released. It begins to move. So now if we consider what are the different forces acting upon the system. Number one, the force of, you can say that first one, restoring force. What are the different forces acting upon the system? That is the restoring force, or in some books it is written as a force of restitution, which is proportional to x. I think all of you know, we can write here f is directly proportional to minus kx. Similarly, another force is acting upon the system, that is the damping force. Or in some books it is written as retarding force. Or resisting force. Which is proportional to the velocity, that minus e dx by dt. That is according to Stokes' law. If you have remember in your school physics, which tells us viscous force depends upon the velocity. Now, according to Newton's second law of motion, the equation of motion of the oscillating particle. The equation of motion of the oscillating particle can be written as these two forces is balanced, which is that inertial force. So we can write this as md square x by dt square equal to minus kx minus p dx by dt. Okay, if you give the equation number 1, 2, then we can give equation number 3. Now you will see that in equation number 3, the negative sign in the first term, that is the first term of right hand side, indicates that the direction of restoring force is opposite to that of displacement. The second one, negative sign in the second term, indicates that the direction of a damping force is opposite to that of the velocity. What are the physical significances of these negative signs? In this case, it is directly proportional to the displacement, that is your restoring force, and damping force is directly proportional to velocity and opposite to that of the velocity, means opposite to that of the motion. So this equation holds only for small displacements and small velocities. So now we can write this equation as d square x by dt square plus p by m dx by dt plus k by m x equal to 0. Okay. So this equation can also be written as d square x by dt square plus gamma dx by dt plus omega 0 square x equal to 0. Or it is not equal to dt. Where this gamma equal to p by m and omega 0 square equal to k by m. This is equation number 5, this is 6. Where omega 0 is the angular frequency of the oscillator in the absence of a damping, which is known as natural frequency of the oscillator. Now if you will check what is the dimension of a gamma and omega 0, all of you will cross check. What is the dimension of a gamma and omega 0? If all of you will check, this is the dimension is T inverse. That is the dimension of a frequency. Omega 0 and gamma. So you will see that equation number 4 is the differential equation of the damped oscillator. Equation number 4 is the differential equation of the damped oscillator. And all of you mark out, it is a second order linear differential equation. It is a second order linear differential equation. Now our aim is to find its solution. First, we will try to find the general solution. Now, your equation number 4 is a second order linear differential equation. Now, we can use the solution of this equation as an exponential function. That means let us take x equal to a e to the power alpha t. Let us assume that x equal to a e to the power alpha t is a solution of equation number 4. I think all of you know that if equation number 7 is the solution of equation number 4, then equation number 7 should satisfy equation number 4. Everybody clear? If equation number 7 is the solution of equation number 4, then equation number 7 should satisfy equation number 4. That means the value of x should satisfy this equation number 4. So if x equal to this, find out the value of dx by dt. That will be alpha a e to the power alpha t and d square x by dt square. That is alpha square a e to the power alpha t. So if this is 8, 9, now substitute equation number 7, 8, 9 in equation number 4. Substituting equation number 7, 8, 9 in equation number 4. Then we will get alpha square plus gamma alpha plus omega 0 square a alpha t, sorry, a e to the power alpha t equal to 0. Very clear? Then we see equation number 10 is valid for all values of t. Equation number 10 is valid for all values of t. Hence, now you see it contains two terms. One is within a bracket, another is a e to the power alpha t. Now, since we have taken a e to the power alpha t as the solution of equation number 4, hence this cannot be 0. Only what is present within the bracket, that can be 0. Since equation number 10 is valid for all values of t, hence the term in the bracket must vanish. That means we can write alpha square plus gamma alpha plus omega 0 square equal to 0. You have to write why this cannot be 0 and why only that alpha square plus gamma alpha plus omega 0 square equal to 0. You have to explain. Not only that what is present in mathematical equations. I think all of you know that mathematics is the language of physics. Till then you have to give the physical interpretation of these mathematical equations. So now since it is a quadratic equation, I think all of you know that we can get two solutions. That is your alpha 1, I can write like minus gamma by 2 plus half gamma square minus 4 omega 0 square to the power half. Similarly, alpha 2 can be written as minus gamma by 2 minus half gamma square minus 4 omega 0 square to the power half. So equation number 12 and 13 are two roots of equation number 10. So equation number 12 and 13 are two roots of equation number 11. Now, again we see that since equation number 4 is a second order differential equation, since equation number 4 is a second order linear differential equation, it has two solutions. So these two possible solutions, we have taken the solution of equation number 4 as x equal to a e to the power alpha t. Yeah, initially we have taken. Now we have got two values of alpha, that is alpha 1 and alpha 2, which are given in equation number 12 and 13 respectively. So we can write two solutions. The first one we can write x1 a1 e to the power alpha 1. Similarly, x2 equal to a2 e to the power alpha 2. So now we can write two solutions x1, that is a1 e to the power alpha 1t, which can be written as a1 exponential minus a gamma by 2 plus a half gamma square minus 4 omega 0 square to the power half into t. And the second solution may be x2 equal to a2 e to the power alpha 2 2. We can write a2 exponential minus a gamma by 2 minus a half gamma square minus 4 omega 0 square to the power half t. Everybody clear? If you have any doubt, you can ask. Now you see equation number 4 is a linear second order. Equation number 4 is a second order linear differential equation. Clear? Now we have obtained two solutions. One is given by equation number 14, another is given in equation number 15. That is x1 and x2. Again we know, according to that linear superposition principle, if x1 and x2 are two solutions of a linear differential equation, then its sum x, which equal to x1 plus x2, is also a solution of that linear differential equation. Everybody clear? Again you note down, if x1 and x2 are two solutions of a linear differential equation, then according to the superposition principle, their sum x, which equal to x1 plus x2, is also a solution of that linear differential equation. Already we have read it is applicable only to linear equations. Since equation number 4 is a second order linear differential equation, second order, it has two solutions. Since it is a linear differential equation, x, which equal x1 plus x2, is also a solution of that linear differential equation. Everybody clear? So now we can write the general solution x as x1 plus x2. We can write the general solution of which one? Anybody who can say? We are trying to find the solution of what? Anybody? We are trying to find the solution of what? Hello? Anybody who can say? We are trying to find the solution of what?
So the second order differential equation.
Damped oscillation equation.
Yes. That differential equation of a damped oscillator. That is given by equation number 4, I think so. Okay. So now we can write the general solution. X equal to x1 plus x2. That is a1. You can write this plus this. That 14, right hand side of a 14 plus 15. So a1 exponential at minus a gamma by 2 plus a half gamma square minus a 4 omega 0 square to the power half t plus a2 exponential minus a gamma by 2 minus a half gamma square minus a 4 omega 0 square to the power half t. Okay. Where a1 and a2 are arbitrary constants to be determined from the initial conditions. Now, depending upon the nature of alpha 1 and alpha 2, this portion is alpha 1, this is the alpha 2. Now you see, if gamma is greater than 2 omega 0, this will be positive. If gamma equal to 2 omega 0, this term will be 0. If gamma is less than 2 omega 0, this will be imaginary. So in this way, so depending upon the nature of alpha 1 and alpha 2, we will get 3 different cases or 3 different types of solutions. Very clear? So there are 3 different kinds of motion depending upon the nature of alpha 1 and alpha 2. Now we will consider these 3 different cases one by one. First one. So this is the general solution. You have to remember this solution because always we will discuss this general solution. When we will consider different special cases, we will substitute our conditions in these general solutions. Okay. Now case 1. When we will consider gamma greater than 2 omega 0. What is gamma? Gamma is the damping coefficient. If the damping is more, it is the case of a large damping. It is the case of large damping, which is also known as over-damped motion. Over-damped motion. Now we will substitute these conditions in our general equation of motion. General solution. If gamma greater than 2 omega 0, then we can write gamma square by 4 minus omega 0 square to the power half equal to some positive constant. Is a positive quantity. Suppose that positive quantity we have denoted by Q. This is a positive quantity. Positive quantity, we have taken this positive quantity as Q. Positive real quantity. So now we can write the general solution or displacement of that damped harmonic oscillator. We can write A1 exponential minus a gamma by 2 plus Q into T plus A2 minus a gamma by 2 minus a Q into T. So we can write A1 exponential minus a gamma by T2 into A1 e to the power Qt plus A2 e to the power minus Qt. Now let us substitute A1 plus A2 equal to C and A1 minus A2 equal to T. Let us substitute A1 plus A2 equal to C and A1 minus A2 equal to D. Then we can write A1 as C plus D by 2 and A2 as C minus D by 2. Hence, substituting equation number 19 in 18. Substituting equation number 19 in 18, we can write x equal to exponential minus a gamma t by 2, c plus d by 2, e to the power qt, plus c minus d by 2 e to the power minus qt. So this can be written as e to the power minus a gamma t by 2 into c e to the power qt plus e to the power minus qt by 2 plus d e to the power qt which can be written as here x equal to e to the power minus gamma t by 2 into c cos hyperbolic qt plus d sin hyperbolic qt. So equation number 20 is the equation of motion for a damped harmonic key oscillator in case of a large damping or over damped motion. So this equation number 20, represents a motion which is non-oscillatory, aperiodic, it is non-oscillatory, decreases, and not periodic, as well as it is also known as dead beat, over damped, or in some books it is written also that heavily damped. In our book, we have collected different names from different books and we have written all these names. It is a non-oscillatory and aperiodic motion, which is also known as dead beat. I think all of you have read about that moving coil galvanometer. You have read in your 10 plus 2 classes, where this displacement decreases or decays exponentially with respect to time. I think you have done that experiment. That is the case of moving coil galvanometer, or a pendulum immersed in a highly viscous fluid. The example of overdamped or large damping. This type of motion is found in an aperiodic moving coil galvanometer or a pendulum immersed in a highly viscous fluid. A pendulum immersed in a highly viscous liquid.
Sir,
Yes.
স্যার হাইপারবোলিক কিউটিটা স্যার ওটা কি করে এলে এটা বুঝলাম না স্যার, এটা দিয়ে
Like e to the power ix plus e to the power minus ix by 2 is the sin x. Similarly, it is the hyperbolic function. I think you have read like trigonometry function. You have read a hyperbolic function. This is the nature of the hyperbolic function. Relation between exponential function with that hyperbolic function. You can go through the book or any mathematical physics book. It is given hyperbolic function, or from website also you can get the nature of hyperbolic function. Like your e to the power ix plus e to the power minus ix by 2, that is the sin x. Similarly, here e to the power qt plus e to the power minus qt by 2 is the cos hyperbolic qt, and this one is sin hyperbolic function. Hyperbolic function you can study from mathematical books, that hyperbolic function, or from website also you can study. Then case 2. So this is non-oscillatory aperiodic motion. Now case 2. When gamma equal to 2 omega 0, when gamma equal to 2 omega, sorry, here if you plot a graph, I have forgotten this one. If you plot a graph that is x versus time, then you will get the curve like this. Increases and decreases. This person is visible over here.
স্যার মোটামুটি
Then I am drawing here. Okay, this is the x. This is that. So in this case, you can write one sentence. The displacement after passing its first maximum in this case, displacement after passing its first maximum, decays asymptotically. Decays asymptotically. I think all of you have read asymptotes. This type of. Decays asymptotically to 0. To 0. Then comes to case 2.
স্যার মানে ওভার ড্যাম্পিং এর ক্ষেত্রে একবার ম্যাক্সিমামে গিয়ে তারপর আর চলতেই পারে না,
ডিক্রিজ করে। It decays asymptotically to 0, but it will take time when it will become 0. That is why it is known as damping. In this case, damping is more. That is why it decays asymptotically. Now, when we will consider the case 2, that is gamma equal to 2 omega 0. This is the case of critical damping. This is the case of critical damping. Now we substitute gamma equal to 2 omega 0 in that general solution, that is, I think, equation number 16. Then you will see that that term will be 0, gamma minus 2 omega 0. So we will get x general solution, x equal to a1 plus a2 into e to the power minus gamma t by 2. So we can write, since a1 and a2 are the constant, we can write another constant, e to the power minus t gamma t by 2. Where b equal to a1 plus a2 is a constant. So in this case, we have got, since gamma equal to 2 omega 0, if you see that two roots are same, alpha 1 equal to alpha 2. Alpha 1 equal to alpha 2. And from equation number 22, it is clear that the displacement decays exponentially. In the first case, it was asymptotically, and in this case, it decays exponentially. The motion is non-oscillatory. In the first one case also, we have seen it is non-oscillatory. And you will see that the time taken by the oscillator to return its initial stage depends upon gamma, that is the damping factor. This motion is known as critical damping, and just aperiodic. So in the first case, when damping was very large, in that case also we have got non-oscillatory aperiodic motion. Here also it is aperiodic and a non-oscillatory motion. And in the first case, it decays exponentially. And in this case, in the first case, it decays asymptotically. In case of a critical damping, it decays exponentially. The example of your over damping is the aperiodic moving coil galvanometer or a pendulum immersed in a highly viscous liquid. Here, the example of a critical now, if you see limited graph also here, that is when t equal to 0, its value will be t. In our, according to mathematical equation, it is b value of x, then it decreases exponentially. Okay. So you will see that the rate of fall of a displacement If you want, you can note down one point. The rate of fall of displacement is much steeper in the case of a critically damped motion. The rate of fall of a displacement is much steeper in the case of a critically damped motion than in the case of overdamped motion or overdamping. So if we make a comparison between overdamped and critically damped motion, displacement will be right like this. In case of critical damping, it decreases exponentially, and in case of over damping, decreases, but initially first maximum value, then it decreases. This is the case of over damped, and this is critically damped. Critically damped motion. Comparative study of overdamped and critically damped motion. Now case 3.
স্যার বলছি তাহলে
Gamma less than 2 omega 0. Case 3. When a gamma less than 2 omega 0.
স্যার
Now you will see. Yes.
স্যার তাহলে ক্রিটিক্যালি ড্যাম্পড মোশনকে ইয়েট টু বি মানে জাস্ট টু বি পিরিয়ডিক কেন বলা হচ্ছে? এটা তো আরো স্টিপার।
Since it is exponentially decreases with one constant is there, and basically you will see that the motion, we are saying that the time taken by the oscillator to return its initial states depend upon gamma, and your e to the power minus a gamma t by 2. So its value will be small in comparison to that of overdamped, because in case of overdamping, the gamma is more. Now in this case, gamma is less in comparison to that one. In both the cases, we are saying non-oscillatory or periodic. But here in this case, damping is, we can say that less than that of overdamped. Okay, now we will discuss about case 3. That is gamma less than 2 omega 0. Then what will happen? If we consider gamma is less than 2 omega 0, that is the case of a small damping. In some books it is written as weakly damped oscillator. In our book we have given all the names. Weakly damped oscillator or under damped. That was over damped. This is under damped. If gamma is less than 2 omega 0, then gamma square by 4 minus omega 0 square will be imaginary. Suppose I omega, where omega equal to omega 0 square minus gamma square by 4 to the power of half. Where we can say that omega equal to omega 0 square minus omega. Now using this value in equation number 16, but we will write x equal to a e to the power minus gamma t by 2 a1 exponential I omega t plus a2 exponential minus I omega t. You can write like this. Now using the identity that already I have said I to the power theta equal to cos theta plus I sin theta, and e to the power minus I theta equal to cos theta plus minus I sin theta. This is your equation number 24, 25. So using this we can write, we see here e to the power I omega t. E to the power I omega t will be cos omega t plus I sin omega t, etc. So substituting equation number 25 in 24. Substituting the identity from equation number 25 in equation number 24, we can write x equal to a e to the power minus gamma t by 2, a1 plus a2 cos omega t plus I, a1 minus a2. Sin omega t. If we substitute a1 plus a2 as a1 plus a2, suppose equal to a cos delta, and a1 minus a2 into I, that is equal to a sin delta. If we substitute this in equation number 26, then what we will obtain? Then we will get x equal to a e to the power minus gamma t by 2 cos delta omega t minus delta. Where already we know omega equal to omega 0 minus gamma square by 4 to the power half. Now you see, so in case of weakly damped oscillator, we obtain the displacement x equal to a e to the power minus gamma t by 2 cos omega t minus delta. Now you see, in the previous two cases, we have got the motion is non-oscillatory. Now you see, here motion is oscillatory due to the presence of a sine or cosine function. Then say it is oscillatory. Clear to this point? It is oscillatory. Whereas in the previous two cases we have obtained, that is known as. Now, you see the amplitude. What is the amplitude? A e to the power minus gamma t by 2. This is the amplitude. Again, you see that since amplitude is not constant and it decreases with time, the motion is not SHM. In case of SHM, we know the amplitude is constant. Again, you see, since its amplitude decreases, it does not repeat itself. It does not repeat itself. That is why it is not periodic. That is why it is not periodic. It is oscillatory, not SHM, not periodic motion. As the damping decreases after each swing. Now, if you will plot a graph, like our previous two cases, that is displacement versus time, then you will obtain the motion like this. After each swing, already we have said this amplitude decreases. Okay. Now, if you are interested, you can note down one or two sentences here. Although the amplitude decreases exponentially with time, the weakly damped oscillator executes some sort of oscillatory motion. The motion is not strictly periodic. Already we have said it is not periodic. So we have to give an explanation like that. The motion is not strictly periodic. However, it has a time period. However, it has a time period t which equal to 2 pi by omega, which equal to 2 pi by omega, which is the time interval. Very carefully note down this point. Which is the time interval between two alternate zeros of displacement. However, it has a time period t which equal to 2 pi by omega, which is the time interval between two alternate zeros of displacement. The time period between two successive zeros of displacement is t by 2. So in this case, what we can give the conclusion? So in this case, what we can give the conclusion? We can say that in case of weakly damped oscillator, the amplitude A0 decreases from A0 to A0 e to the power minus a gamma t by 2, where A0 is the original amplitude. That means when there is no damping. And a decrease in frequency, angular frequency, that omega, your initially omega 0, now it becomes omega, which equal to omega 0 minus omega square by 4 square root of omega 0 square minus this, we can say that omega 0, 1 minus a gamma square by 4 omega 0 square to the power half. The example of a weakly damped oscillation is a pendulum having massive bob oscillating in the air. A pendulum having massive bob oscillating in the air. So these are three different types of damped motion: over damped, critically damped, then weakly damped motion, and their equation of motion also. Then in the next class, we will discuss about energy of a weakly damped oscillator. Energy of a weakly damped oscillator, that in the next class we will discuss.